The fastest object ever built by humans has been traveling for half a century. Voyager 2 launched in 1977. It has spent 47 years moving steadily through the emptiness of space, covering just over 140 astronomical units. That's 140 times the distance from Earth to the Sun. It sounds impressive, until you try to map that distance to the nearest star. That star is 270,000 times farther away. At its current speed, Voyager would take about 70,000 years to reach Proxima Centauri. Imagine someone stepping out of a cave in the Neanderthal era and only now arriving at the next apartment building. Here's what doesn't add up. We send rovers to Mars. We capture images of black holes. We collect samples from asteroids and bring them back to Earth. Every year brings a new headline, a new record, a new mission. Progress feels real, solid, and tangible. But look beyond, just a little past our solar system, and all that progress shrinks to a point indistinguishable from zero. Konstantin Eduardovich Tsiolkovsky put it with surgical precision. There are only two paths. Either Earth is both our cradle and our grave, or we find a way to reach other worlds and spread across the universe. He never saw a third option. Let's be honest, most of us, myself included, have long assumed the choice was already made. We're flying, we're building rockets. But Tsiolkovsky wasn't talking about just orbiting our own planet. He envisioned leaving the cradle behind. And so far, we haven't left it. Even Voyager, with all the romance of its golden record, is just drifting, uncontrolled, unable to slow down, not heading anywhere in particular. A message in a bottle tossed into the ocean from the shore. And that's where a simple question comes up. What if we didn't have to burn fuel? What if we could harness light, the free, endless energy of sunlight, as the wind for a sail? It's a beautiful idea. Photons strike a thin, mirrored film and transfer their momentum. The spacecraft accelerates. No fuel, no tanks. Here's what happens to that sail as it moves away from the sun. The pressure from sunlight drops off with the square of the distance. Move twice as far and the pressure falls to a quarter. 10 times farther and it drops to 1/100th. Simply put, the farther you get from the star, the weaker the push becomes. At the distances where true interstellar travel begins, that push fades to a whisper. And then, silence. It's a vicious cycle. Rockets move too slowly. The solar sail loses strength just when you need it most. Physics seems to slam the door shut. But sometimes, hidden in the very laws of physics are loopholes, in those formulas that seem to forbid everything. And some people with deep pockets believe they know exactly where to look. NASA was the first to try. In 1996, the agency launched a program with a bold name, Breakthrough Propulsion Physics. The mission was daring, to discover radically new ways to travel through space, not to improve existing rockets or squeeze extra performance from chemical fuel, but to find something fundamentally different. 6 years passed, dozens of ideas came and went, not a single breakthrough. Then, in 2002, the program quietly shut down. No press conferences, no explanations. They simply stopped funding it. The world's largest space agency threw up its hands and stepped back. Then, onto this empty stage stepped a man of a completely different caliber, Yuri Milner, a Russian-American billionaire who made his fortune by investing early in tech companies, decided that the challenge of interstellar travel simply needed the right people and enough funding. His goal sounded like a line straight out of science fiction: to build a probe that could reach the nearest stars within a human lifetime. Not thousands of years like Voyager, not centuries, just 20 to 30 years. And he assembled a team to match. Martin Rees, the United Kingdom's royal astronomer, Freeman Dyson, one of the greatest theoretical physicists of the 20th century, Stephen Hawking, a name that became synonymous with genius for millions around the world. When figures like these sit down at the same table, a breakthrough feels inevitable. It's only a matter of time. Their idea was elegant on paper. Take an ultra-thin sail, lighter than a butterfly's wing, spanning just a few square meters. Embed tiny microchips into it, cameras, sensors, a transmitter. In 2016, they even showcased a prototype, a translucent film with minuscule electronic circuits inside, weighing only a few grams. It looked stunning, like a shimmering napkin, but every square centimeter cost as much as a high-end laptop. Now comes the main trick. This sail doesn't rely on sunlight. Instead, a ground-based laser beams 100 gigawatts of power onto it. 100 gigawatts. That's like the combined output of 100 large nuclear power plants, focused into a single beam. The beam hits the sail, pushing it forward. According to estimates, it can reach up to 20% of the speed of light. That's 60,000 kilometers per second. At that speed, a trip to Alpha Centauri, the closest star system, would take about 20 years. That fits within a human lifetime. Sounds like a plan. But this is where the questions start. Questions that could unravel the whole idea. 100 gigawatts. Where do you even find a laser like that? It doesn't exist yet. We have to build it. And even the most optimistic estimates put the cost on par with the Large Hadron Collider, around $10 billion. Actually, it's probably more. The collider at least used an existing tunnel, but this laser array would have to be built from scratch. $10 billion just for the light source, not for the sail, not for the guidance systems, not for the receiver stations to catch the signal coming back over 4 years later. And there's another issue engineers don't talk about as openly as the budget. A laser with 100 gigawatts of power is effectively a weapon. A beam capable of pushing a sail to 20% the speed of light could also destroy a satellite in orbit, or a city. Which government would greenlight building something like that? And which government would allow another to build it? Let's be honest, my friends. When solving a technical problem stalls not because of physics, but because the resulting device could be used as a strategic weapon, that's no longer an engineering challenge. It becomes a political dead end, one that equations can't solve. Milner's project never officially shut down. Instead, it just stopped making progress. They unveiled a prototype sail to the press. Stephen Hawking spoke at a press conference. Stunning renderings spread across all the popular science websites. But the laser? It stayed nothing more than a number on a slide. But what if there's another way? Not to fly to the stars, but to study them up close, from right here. This idea actually exists, a solar gravitational lens telescope. Here's how it works. The sun's massive gravity bends space around it, acting like a colossal lens. Light from distant objects passing near the sun converges at a point behind it. If we position a receiver at that focal point, we could capture images of exoplanets with a clarity no Earth-based or orbiting telescope can match. The challenge lies in pinpointing that spot. It's roughly 1,000 astronomical units from the sun. To put that in perspective, 1,000 astronomical units is 25 times farther than Pluto. The Voyager 1 spacecraft took 46 years just to reach 160 astronomical units. We need to go 6 times farther. At current speeds, a probe would take over 2 centuries to get there. No one pressing the launch button today would even live to see a quarter of the journey completed. 2 massive projects stand before us. One demands a laser the size of a small country, with a budget bigger than any nation's space program. The other requires patience that stretches beyond a human lifetime. Both hinge on the same logic. When a problem won't bend, you bring more power, more money, more scale. You try to conquer the universe with sheer force. But right here, at the distance of Earth from the star, 1,400 watts of solar energy hit every square meter of space. Free. Every single second. Maybe, instead of spending $10 billion on building a laser, we should ask, is there a way to capture this energy, just differently than we've tried before? It's possible. David Kipping, a physicist at Columbia University, is focused on exactly this, finding ways to make the expensive affordable. Not through breakthroughs, new materials, or engines, but by asking, what are we already using wrong? In 2019, he introduced a concept called the terryscope. The idea sounded almost like a joke. Why build a telescope with a giant lens when we already have a lens 12,700 kilometers wide, the Earth's atmosphere? As sunlight grazes through the atmosphere, it bends and focuses on the far side of the planet. Place a receiver in just the right spot, and you could get a zoom 150 times greater than any ground-based telescope. No need to build a mirror. No need to launch anything into orbit. The lens is already hanging overhead. Nobody just thought to look through it from the right angle. This is a typical move for Kipping. Not inventing something new, but noticing what's already there. Here, we should pause and focus on a single number we've mentioned before, but haven't fully grasped. 1,380 watts per square meter. That's how much solar energy hits every square meter of space at 1 astronomical unit from the Sun, basically where Earth orbits. Imagine a powerful hairdryer blowing straight in your face. Now imagine that hairdryer is a square meter wide, and it never turns off. Never. Day and night, winter and summer, for billions of years, the flow never stops for even a second. Free energy flooding every inch of the space around us. The problem with solar sails is that they try to harness energy head-on. Photons push against the sail, accelerating it, and the spacecraft blasts away from the sun. But the farther it gets from the star, the weaker the light becomes. At Jupiter's distance, the power drops from 1,400 watts down to just 50. By the time you reach Pluto, it's less than 1 watt. The sail takes off with a burst, but immediately starts running out of fuel. So it comes down to a simple choice. Either build a massive laser to make up for the fading sunlight, spending billions in the process, or accept that the light grows weaker and settle for a snail's pace. 2 options, both dead ends. David Kipping saw a third way. What if you didn't fly anywhere at all? What if you stayed right here at 1 astronomical unit, where the sunlight is strongest, and just stored energy instead? Instead of pushing the spacecraft forward, you spin it in place, like a flywheel. The flywheel is an ancient concept. Think of a potter's wheel spinning on its own after you lift your foot off the pedal, or a child's spinning top. The principle is the same. You add energy in bursts, and the flywheel stores it as rotational motion. Slowly, turn by turn, its speed builds. The energy doesn't fade. It accumulates in the mass spinning faster and faster. David Kipping's idea revolves around this exact principle. Instead of gathering solar energy by moving away from the sun in a straight line, you store it as kinetic energy in rotation. The device stays fixed at a set distance from the star. Photons press against it every second, and each second it spins a little faster. It doesn't fly off. It doesn't speed up in a straight path. It just gains momentum, day after day, month after month. Then, when the flywheel reaches its limit, it lets go. Here's the crucial question that everything hinges on. Any object orbiting the sun follows Kepler's laws. It has to move at a certain speed, or it will either crash into the star or drift endlessly into space. So how can you make a structure weighing several kilograms just hang in place, year after year, without falling prey to gravity? The answer is simple, and yet counterintuitive. The structure holds itself up through light. 2 ultra-thin sheets of material, connected by a cable, slowly spin in the void, circling the sun at a distance of 1 astronomical unit. One side of each sheet shines silver and mirror-like, reflecting photons. The other side is dark, absorbing them. Light presses against both sides, but differently. The reflective side bounces photons back, gaining twice the push. The dark side soaks them in, getting only half that force. This difference in pressure creates a twisting force. The whole setup begins to rotate, slowly, almost hypnotically, without a single engine, without fuel. Just light and geometry. But rotation is only half the challenge. The other half? Not falling into the sun. In physics, there's a theoretical concept called a statite. It's a structure where the pressure from solar radiation perfectly balances the star's gravity. A statite literally hangs suspended in space, not orbiting, not in free fall. It just floats, like a balloon stuck under a ceiling. Gravity pulls it down, the light pushes it up. The forces are equal, zero movement. The catch? The perfect statite exists only in theory. We can't build one from real materials yet. The surface would have to be incredibly thin and highly reflective, beyond what any material we have can achieve. And here Kipping makes a clever move. His design isn't static, it's quasi-static. The sail is thin and reflective enough that the pressure of sunlight cancels out most of the gravitational pull, but not all of it. The remaining gap is made up by a tiny orbital speed. In other words, the craft still orbits the sun, but much slower than any typical object at the same distance. Kepler's laws dictate a certain speed for any orbit, but this quasi-static sail moves noticeably slower. That's because it doesn't have to run as fast. The light itself lifts much of the gravitational weight. It's like a runner on a track catching an invisible tailwind pushing them forward. They no longer need to sprint full force, just a light jog to stay on course. Now, let's talk about the actual dimensions. The design measures 7 meters wide and 63 meters long. That's about half the length of a football field, stretched out into a narrow strip. Its thickness? Less than 3 microns. Thinner than plastic wrap, thinner than red blood cells. The material consists of sheets made from carbon nanotubes. The entire structure weighs just 1 6/10 kilograms, about the weight of 1.5 cartons of milk. Yet it can carry a payload, a chip 10 by 10 centimeters in size. This entire interstellar sling weighs less than a domestic cat. Launching 1.5 kilograms into orbit is no big deal by today's space standards. No mega rockets, no multi-billion-dollar budgets. But this is where things get really interesting. The structure reaches orbit. Photons press against its shiny and dark sides. The difference in pressure creates a twisting force. The panels begin to spin. After a week, the rotation speeds up slightly. A month passes, a bit more acceleration. 6 months in, the structure spins noticeably faster. After a year, even faster. The sun doesn't go anywhere. Photons keep pushing. No energy is lost. It builds up with every turn, like a spinning flywheel. By the end of the second year, the outer edge of the ribbon moves at speeds measured in kilometers per second. By the middle of the third year, it approaches 12.1 kilometers per second. That's the limit. Not the limit of solar pressure, not the limit of orbital mechanics. It's the strength limit of the carbon nanotubes. The material making the sling has a finite tensile strength. After 3 years of constant acceleration, the centrifugal force nears the threshold where the nanotubes will start to break. For 3 years, this fragile strip of carbon soaks up sunlight, spinning faster and faster. Then, one day, the moment comes when the material can no longer hold together. The nanotubes snap, not just anywhere, but exactly where we predicted. The centrifugal force surpasses the material's strength, tearing the structure apart. But one piece isn't just debris. It's a microchip, a 10 by 10 centimeter wafer of silicon and electronics that has waited 3 years for this very moment. The rotational energy, building up with each spin, suddenly converts into straight-line motion in a fraction of a second. The chip detaches from the edge of the strip and shoots off tangentially, like a stone from David's sling. Only here, the sling stretches half the length of a football field, and the stone doesn't fly at Goliath, but shoots out of the solar system. At liftoff, the speed hits 40.5 kilometers per second. That's not just a random number. The solar system's escape velocity, the speed needed to break free from the sun's gravitational pull forever, is exactly 40 kilometers per second. This chip surpasses that threshold by half a kilometer per second. Simply put, even the basic version of this design, built from carbon nanotubes without any enhancements, can already propel a probe into interstellar space. Not just theoretically, mathematically. But why stop at math when you have orbital mechanics? The path the craft takes around the sun doesn't have to be a perfect circle. If you send it on a stretched out elliptical orbit with a high eccentricity and then release the chip at perihelion, that is, at the point closest to the Sun, the probe's speed combines with the orbital speed of the entire setup. It's the same idea behind a hammer thrower spinning faster before letting go. The faster the thrower moves at release, the farther the hammer flies. Only here, the star's gravity plays the role of the thrower. And then there's Jupiter. A gravitational slingshot around the largest planet in our solar system is a tactic proven over decades. The Voyager probes used it back in the late 1970s, gaining more than 10 extra kilometers per second at no fuel cost, thanks to Jupiter's gravitational pull. The same trick works here. Aim the chip to pass close by the gas giant, steal some of its orbital energy, and speed away even faster. Here's the interesting part. All those tricks, elliptical orbits, gravity assists, add speeds in small increments. 10 kilometers per second here, 5 there. But the real barrier lies somewhere else entirely, and it's not orbital, it's physical. To launch a chip faster, the structure has to spin harder. To spin harder, the material must withstand greater centrifugal forces. Carbon nanotubes snap when the outer edge reaches about 12 kilometers per second. You could use high-quality graphene. It's stronger, letting the device store more energy and reach higher revolutions before breaking. That raises the bar. But it doesn't eliminate it. Every material, no matter how tough, has a finite breaking point, and centrifugal force grows with the square of the rotation speed. Sooner or later, it wins. Every time. It might seem like a dead end. Material physics sets a hard limit. No graphene, no carbon nanotubes, no future supermaterials can break through it. They can only push it up a bit. But what if, instead of fighting centrifugal force with strength, we fight it with another kind of force? This idea turns the whole design on its head. Opposite ends of the ribbon carry opposite electric charges. Positive on one side, negative on the other. Opposite charges attract. That's something anyone who's rubbed a balloon on a sweater knows. The electrostatic force pulls the ribbon's sides together, acting directly against the centrifugal force trying to tear them apart. What emerges is an internal framework made of electricity. Invisible, weightless, but very real. The material no longer carries the load alone. It gets help from Coulomb attraction. Here's what this means. A structure reinforced by electrostatics can spin up to 12 kilometers per second. Not 50, not 100. The theoretical top speed for launching a probe with electrostatic boost hits 1,000 kilometers per second. That's 0.3% of the speed of light, 25 times faster than the basic version. The strength limit of carbon nanotubes, which just a minute ago seemed like an unbreakable barrier, turned out not to be a wall, but a door. You just needed the right key to unlock it. And this key isn't new material. It isn't a new engine. It isn't new physics. It's electricity, applied in just the right direction. The very same force that makes your socks stick together after a tumble in the dryer here holds a space sling together at speeds that would crush any material in the universe to dust. And yet, the structure still runs on sunlight, weighs less than a house cat, and fits inside the cargo bay of a standard rocket. Traveling at 1,000 kilometers per second sounds like science fiction, but the equations prove it's possible. Now, there's only one question left. What does this mean for our future? The most fascinating thing about technology isn't what it was originally designed for, it's how people find new uses for it later. The electrostatically enhanced TARS converts solar energy into a magnetic field. That's its primary job, to keep the ribbon from tearing. But magnetic fields are incredibly versatile. If a device can generate one in space, powered solely by sunlight, it can create localized magnetic shields. Placing several of these units in Mars's geostationary orbit could produce protective fields against ionizing radiation right above future colonies. Mars doesn't have its own magnetic shield. Anyone stepping onto its surface faces constant bombardment by cosmic rays. Just 1.5 kilograms in orbit, and suddenly the colony has a shield. Not perfect, but real. Now, let's take it a step further. Instead of launching a single probe, imagine sending a series, each one following the last, just a bit behind. They line up like a chain. Each probe turns into a relay station. The signal jumps from one to the next like a baton passed in a relay face. This creates a data relay network, a kind of interstellar internet, not just a metaphor, but a real engineering proposal. But let's be honest, this system isn't a perfect fix for interstellar travel. It's slow. Even at 1,000 kilometers per second, reaching the nearest star would take more than 1,000 years. And it can only launch tiny probes. No crews, no tons of scientific gear. Just chips, sensors, and tiny transmitters. Still, remember how this conversation started. The Breakthrough Starshot project, $100 million for research, a gigawatt-scale laser array, an emitter spanning a square kilometer. The construction budget runs into tens of billions. No government is ready to fund that yet, but right next to it, there's a design weighing just 1.5 kilograms. Solar panels, a ribbon of carbon nanotubes, electrostatic amplification, existing materials, existing technology. The budget of a small private lab. No involvement from major space agencies, no gigawatt lasers, no international consortiums. What once seemed like a task for an entire civilization turned out to be a challenge a small team of engineers could handle. The first step toward the stars might not look the way we imagine. Not a massive ship carrying 1,000 passengers, not the flash of a thermonuclear engine visible from Earth with the naked eye. Instead, a quiet snap, like a released slingshot, and a tiny chip shoots into the darkness at a speed that, just 10 years ago, seemed impossible. We don't yet know if it will make it, but for the first time in history, the question isn't, is it possible? It's, when exactly will we do it?